Today we're going to talk about geometric sequences. Geometric sequences are similar to arithmetic sequences in that there is some sort of a common number that helps them increase or decrease. The difference between geometric and arithmetic, however, is that arithmetic is basically linear, written in a different way. Geometric is not done with addition or subtraction along the way. Like the recursive formula wouldn't be plus 1, plus 1, plus 1, and so on. It might be times 3, times 3, times 3, or divided by 7, divided by 7, divided by 7. So we're using a different operator. We're using multiply or divide, and either one of those will make a geometric sequence. Let's get right into it. You should have 9.3 notes for geometric sequences open. The highlighted stuff in pink is the stuff we're going to go over. So let's begin right away. I'll write in blue today, and it says in the beginning, determine if a sequence is geometric. So let's talk about how that works. By the way, I'm going to do a lot of calculating today, so I am going to, let's do this correctly. I'm going to have my calculator open, kind of off to the side, but I'm going to use that calculator regularly today when I need it. So let's start with the first one. What I'm looking for is I'm looking for a ratio that is consistent. So here's how I'm going to do this. I'm going to draw the arrow just like I did with arithmetic, but I'm going to take the 6 and divide it by 1. 6 divided by, in this case, -1. And then I'm going to take the next one, and I'm going to take the -36 and divide it by the +6. I'm going to do it one more time. 216 divided by -36. Now, in these, I'm not going to use the calculator because I don't think any of us need that. What I think we're going to find is that each one of these, when they divide, equals -6. That means it's geometric, okay? It's changing by a factor of -6, and I'm going to use factor as a multiplier. So -1 times -6, 6 times -6, -36 times -6, and so on. So it's not plus or minus, it's multiply or divide. All right, that's how you determine if a sequence is geometric. If you divide those numbers out and they do not come out to have a common factor, then they're not geometric. Simple enough. Now, there are two different types of formulas. There's recursive, which we're not really going to cover in this video, and there are explicit. We've talked about why explicit seems to be better in most cases. So let's go ahead and stick with explicit formulas for now. I have the explicit formula already written down for you. And here's what we have. We have a sub n, or we might sometimes call it y. A sub n, which is going to be what some number in the sequence is going to be. Here we go. This a value is the initial condition. So whatever the first number is in the sequence, or the first number we're aware of, I guess. Ooh, I'm getting advertising. All right, well, I guess I'll let that go. So the initial condition is going to be your first value. The R value is going to be the ratio. In that previous question we just did, -6 would be the R value. And, well, that's pretty much it. Whatever value we're looking for, we take one off of that and that becomes our exponent. So if you're thinking that these look a little exponential, you wouldn't be crazy in thinking that way. So let's keep on going. Let's imagine that we need to find the 10th term in a sequence. Now, we'll do another, we might as well stick with the same one. We've already done this first one part way. We've established that the common ratio is -6. We have our initial condition of -1. So I'm going to write a sub n is our initial condition times the r, which in our case we determined was -6, to the n-1 power. So we want the 10th term, so it's the 10-1 power, or you could probably guess the 9th power. So a sub n is -1 times -6 to the 9th power. And I'm going to go ahead and use my calculator on this one. I'm going to do -6. The way I believe this is worded, we want to put that in parentheses because we might get a negative answer. So I'm going to go ahead and put parentheses -6 raised to the, I don't use this calculator very often. Where's the power button? I don't see the power button. Huh, I don't see the power button. Where's the power button? Oh, maybe I need to have the whole thing open to get to the power button. So up to the 9th power is huge. All right, so let's go ahead and pull Notability back and get it rolling again. So sorry for the delay there. So it looks like this number is going to be, oh, and I guess that's just the -1 times, so -10 million 77,696. And then I'm going to multiply that by -1 because that's my initial condition. So 10,077,696 would be the 10th term. That's massive. But if we are going up by that explicit formula, then that's in fact what we get. So with that in mind, let's move on to some additional pink stuff. I'm going to scroll down, and you should too, to the next thing that is listed. Now, I wrote it in black. It's not on yours, but you should write down that this next little piece is a description of a geometric mean. Now, an arithmetic mean is when you add two numbers, you divide them by, well, if it's two numbers, you divide by 2, and you find the number exactly in between. Well, the geometric mean is similar in that you want to find the number in between them, but not exactly in between. You want to find the number in between them that has the same ratio as you go from the first to the middle, middle to the second. We want, or first to middle, middle to third, I suppose. We want to find that common ratio. So let's look at an example that I have created right here. I'm going from 12 to blank and then blank to 3. And while many of you are very smart and you would figure this out on your own, I want to give you a cool little formula. The cool little formula is this. If the first term in a geometric mean problem is x, and the second term is y, so that would account for any two numbers on either side of a middle piece. The geometric mean is x times y and then the square root, which is pretty cool. So what I'm going to do here is apply that formula instead of really doing anything else. I'm just going to do 12 times 3. I'm going to get 36. I'm going to go ahead and take the square root of 36, which we all know to be 6. And I'm going to go ahead and test it. I'm going to use a highlighter tool to kind of bounce the item. So 12 divided by something is 6. We know that's 2. And 6 divided by that same 2 equals 3. So we have a common ratio of 2, and that 6 makes sense there. So I like it. Great. That's how you do a geometric mean, right? You do this little new formula here, the one that's circled. You take the two outsides, you multiply them, you take the square root, and that'll give you the inside. But what happens if you have more than one space? What if we did the first term was -2, like we do have in number 25, and the second term and the third term and the fourth term were all missing, but you have the fifth term to be -512. All right, well, we do have a middle, so I don't see any reason why we couldn't do that same routine, right? We would take -2 times -512, and we take the square root. And that would be 1,024, and the square root of 1,024 is, I have this backwards because that's how some other calculators work. The square root of 1,024 is 32. Now, interesting here, the 32 could be positive or negative because geometric sequences could be divided by or multiplied by a negative or a positive. So sometimes you'll see flip-flopping signs. So I would probably say that this could be positive or it could be negative at this point. Maybe it couldn't be positive the more I think of it, because I have to get from -2 to a number, and then from that number to the 32. And if everything is negative, then the 32 would be negative. And if it flip-flops, it's going to go negative, then positive, then back to negative again. So the more I think about this, the positive 32 doesn't really make any sense. So I'll take that out. But that is something to keep in mind, though. There might be times when you might find yourself getting more than one answer. Just keep it in mind and kind of be aware of that. I suppose the final step could be, to finish this off, though we're not going to do it right now, is if you could use this one and this one with this formula to get the middle term, there's no reason why you couldn't use these two to get the middle term here, and then these two to get the middle term here. So if you can do that x times y and square root, you can do x times y square root a couple times, and you can find all of the missing values. Now, let's keep this video short. I have one more question, and the truth is, I think we're going to wrap this up. I'm at 9.5 minutes now, so let's get this moving. Last question is number 48. It says, suppose a balloon is filled up with 5,000 cubic centimeters of helium. It then loses 1/4 of its helium each day. Already I'm thinking exponential because I'm decreasing it by 25% a day. But if we're going to stick with this new theme, let's go ahead and see what we can do. I have a to the n is my initial statement. My change is going to be, my ratio is going to be dropping by, well, let's see. If we go 5,000 and then we take 75% of that, oh, I should have multiplied. So 5,000 times, I did it again, 0.75. I'm going to go ahead and get 3750, right? So 5,000 to 3750. Let's take the 3750 and let's multiply it by 0.75. And I'm going to get 2812.5. And I'm going to do it one more time. 2812.5 times 0.75. What I'm trying to do is establish a number of pieces of the sequence. I have I have 2109.375. And because I did this earlier, when I divided 5,000 divided by 3750, I'm going to get 1.3 repeating, right? That's what I need to divide by to get from one to the next. And it turns out that the next one is 1.3 repeating also, and the next one is 1.3 repeating also. And because they're always 1.3 repeating, this is geometric. So here's what I can do. I can write my sequence. It says, how can you write a sequence of numbers representing the situation? We just did this. We just created the values exactly the way the problem described. I took 5,000 and then I decreased it by 1/4 each time. I could have just divided by 4. That would have worked as well. Second little bullet point, is the sequence arithmetic, geometric, or neither? And I'm going to go ahead and say that I believe it's geometric because my ratio is common. Sometimes it could be arithmetic, but this one is not. This one is geometric. And last bullet point, how can you write a formula for the sequence? Here we go. So I'm going to do initial condition is my 5,000. I'm going to multiply by my common ratio, 1.3 repeating, or you could do 4/3. That would be fine as well. In fact, maybe we like 4/3 so I don't have to worry about repeating decimals. And then we're going to go n-1 as our exponent. So n-1. And that's going to be our direct or explicit formula. With what I've done for you here, I'm sorry, and then I guess we should answer the question, or kind of allude to it. This question here, how much helium would be left in the balloon at the start of the 10th day? So I suppose that's the beginning of the 10th day. So all I'm going to do is put a 10 in this spot. I'm going to use my calculator and we're going to crank that out. I'm at 12.5 minutes. I'm not going to do that on the screen, but I think you could follow along by putting a few things into a calculator and going from there. So with that in mind, we've talked about geometric sequences, geometric means. We've talked about how to take a word problem and write a direct or explicit formula. And most importantly, what a geometric sequence is. So kind of a long video, but it's all we need for today and all we need for the weekend. So good luck with your textbook questions today.